Okay, great. So let's continue our analog to digital conversion with this example that I just glanced over last time very quickly. And hopefully this will make you think about the effect of working in sleep mode and which types of tasks run when. So suppose you have the whole bunch of declarations that you usually have. We have a task timer, so we will have a task that we will be calling once this goes down to 0. We have an ISR, which is simply, well, it will be called, right, when you get out of the you get out of the sleep mode once the analog to digital conversion is done. And then you will actually call this interrupt service routine, and then once this is executed, you go back into the main program. But in sleep mode, you would do the conversion, and in sleep mode, the whole CPU, the MCU, is in sleep, is actually not drawing any energy. So here you have the usual conversion. In this case, we do a 10-bit conversion, and because of that, we are actually going to make full use of the ADC-L and the ADC-H registers. We have the least significant bits of this conversion are in the ADC-L. We convert it, typecast it to integers. We do the same for ADC-H for the most significant bits. And we multiply this by 256 because we already have 8 bits in here, right? So this is 2 to the power 8. And then we can just add those two integers together and have an integer representation of the level at which the voltage is measured. Now we still need to convert this. We can do that in the main program. You can convert this integer representation now into an actual voltage amount. Now suppose this task is executed, and it's a sort of made up, of course. We have that we're going to reset the task timer back to 400, say, and then we know that the previous timer over here will start decrementing this whenever you call this ISR, say every millisecond. Then essentially this task will take the voltage, the integer representation that you computed over here at that particular moment in time. So every 400 milliseconds, say, you take that and you convert it into an actual amount of volts. So we have a reference voltage of 5 volt, and we have 10 levels, so to the power 10, so we divide this by 1024. And you do say some more computation. Let's say it's something taking more, and sometimes it takes less time. Let's say no matter how long the task actually takes, let's assume it always takes less than 200 milliseconds. Why do we do that? Then we know that we don't get into a problem with this particular 400 starting value, because if this would take a lot of time, say 600 milliseconds, then in the meantime the ISR would count is already down to 0, and you would immediately start executing this task one after another. So this is just to eliminate, just to be very rigorous about our specification, this eliminates that possibility. So you really call this task in the main program, and then there is, say, you do some computation for 200 milliseconds, but then there's another 200 milliseconds freely available to you to do other things. So you can do some resource sharing. Now in the main program, we will set up some immunizations. We set up a timer 1 in this particular case, so let me quickly okay, we'll have a look at that. Yeah, remember again why we did that. So I will come back to this in a moment. But here we set up timer 0, and it's set to 1 milliseconds. And in this particular setting, we assume a CPU clock rate, I think, of 20 megahertz. It's one of the previous slides. But anyway, if you set it up like this, then you get that accurate, you get that time. Now, I'm asking always questions, so probably this is a setup that may not exactly be accurate, but it's good to do these kinds of computations and get a good feeling for it. Okay, so approximately 1 millisecond. Now we're going to use this particular timer 1 to measure the amount of time that, well, let me go to the next part. Okay, let me finish my sentence then. We will be using this timer 1 to actually use this counter corresponding to timer 1 to measure how many ticks have lapsed in the main while loop when you go from iteration to iteration. And we're going to ask ourselves, what does that really measure? How many does this particular task that we just talked about, is that counted in the measurement of how many ticks are how many ticks have been progressing? And similarly for these interrupt service routines, do they play a role? So I will make it much more precise in a moment. So let me close the door. So over here we have a few more initializations, and this is the usual stuff, right? We set up effectively our ADC conversion, and with the usual prescaler for the clock, make sure that the right pins are set to input, another prescaler over here. We enable all this. We make sure that we enable the sleep mode. That's what we are interested in, the ADC noise canceller. We execute a special piece of microcode, then we enable all the interrupts, and now we're ready to go. And this is the while loop. So this is where I will have a few questions about. So first, notice that we have effectively one task that we're executing, and you only execute it if the task timer of 400, that was the starting state, goes down to 0. What we want to do is look at this piece of code and this piece of code. We want to measure how many ticks have lapsed between this instruction and effectively this instruction. Now you're only executing sleep CPU and the task itself. So sleep CPU is the micro that pushes your MCU into a sleeping state, but is going to start an ADC conversion, and once that's done, you call the interrupt service routine associated to that. Once that interrupt service routine is finished, you go into the main program to the next point over here. In the meantime, your MCU is out of the sleep state, right? Now, over here we have a piece of code. Here we see a T1 poll before and a T1 poll after, and generally we're really interested in the difference between those two. And if we convert it to seconds or microseconds, then we multiply with how many microseconds one particular tick actually takes. So that's written out here in the comments. And then there is also this particular statement over here. Now notice we are going to update a busy global variable. So we're going to add all those microseconds that have passed in these iterations. And we're interested in, what do we really measure? What does that amount of time represent? So what kind of computations actually happened during these ticks when the T1 timer started ticking? What are these computations? So that's what these next questions are about. So there's some more so let's see here. So we have, so this is an explanation of what I just tried to explain. Here we convert the difference to the microseconds, and we will get to this specific line later on where we put that in there. But now we have a bunch of questions, so I'll move immediately forward to the solutions over here. So I'm interested in the following question. So answer with never, sometimes, or always. Whether the execution times of this, in this particular case, this particular interrupt service routine, whether it's actually included when you incremented the busy signal. So what you measure in the busy signal, the amount of time that lapsed, does it actually include the execution of this ISR of timer 0? So let's have a look back. and maybe you have an idea about this. So we know that timer 0 is, effectively calling this interrupt, indirectly, right, every single millisecond. And the ticks that are being measured in the counter 1 are those that incremented between this instruction and this instruction. So we know that task ADC on its own already takes 200 milliseconds, right? So surely 200 times you have executed the ISR for timer 0. So those executions of ISR 0 are included in the time difference measurement over here. But we also know that task ADC resets its task ADC timer to 400. And that means that this piece of code is only executed when, it's set back to 0, meaning that for another 200 milliseconds, so this executes for say 2 milliseconds, it takes another 200 milliseconds to reduce this particular task counter back to 0. So at that point you just go through these iterations, but you never go in this main body. So during that time you execute ISR timer 0, but those executions are not included in the time measurements from here to here. So that's the reason why we say sometimes. So effectively, say half of the time, you actually take those executions into your measurements, and the other half of the time you don't. Alright, what about this particular ISR? Now, if you go back to that main body again, let's have a look here. Well, wait a minute. Where is that ISR that we're talking about? It's this one, right? Now, what is that one called? That one is called in sleep CPU. But remember, as soon as the ADC conversion is finished, the MCU wakes up out of its sleepy state. That means that all the timers start working, including timer 1. So you start incrementing TC and T1, and during those tick increments, you're going to execute the ISR associated to the ADC conversion. And once that's done, you go to the next instruction, which is calling the task ADC function. So that means that you're actually including this ISR always. So that's always part of these TC and T1 tick increments that you measure in the T1 before and the T1 after pulse. Alright, so what about sleep CPU itself? So let's be a little bit more into detail. So the datasheet writes that for the ADC noise reduction mode, that in that particular sleep mode, right, a certain number of peripherals are still working, but others are not. So here's listed what is working. We had seen a table that also explained that. But the conclusions, this means that all the other hardware modules stop working, in particular all the other timers and counters stop working. So that means that actually the execution of going into the sleep mode, right, and then doing that conversion, which represents this particular part, right, so it's literally this piece of macro code is putting your MCU to sleep, starts the ADC conversion. Once the ADC conversion is finished, a flag is set that it is finished, then you drop out of this, then you wake up the MCU again, and that finishes this execution. But since the flag is set of that you finished the ADC conversion, the interrupt associated to the ADC conversion is immediately called after that. So, but the But what is happening in this execution, which is effectively the ADC conversion itself, is done while the MCU is completely asleep. So during that time, TCNT1 is not incrementing its ticks at all. So if you are measuring the before value of TCNT1 and the after value, you look at the difference, then those ticks only represent increments that were outside, that were executions that happened outside sleep CPU, and that's why this is not included ever in that busy signal. So what about task ADC? Well, in this particular case, always, because the ADC task is clearly part of the wrapper that we have. So let's go back quickly at this particular body. Yeah, we are out of sleep mode. All the clocks, all the timers work again, including timer 1. So yeah, the execution of task ADC during its whole execution, TCNT1 will be incrementing all the time. So yeah, why do I put a question like this out there, and with a similar one I think in one of the problem sets? It is because it will make you think about the internal working of all these different hardware modules and how they influence one another. In this particular case, the execution flow. So let's go forward, because there's one more question that I have here, which is, can we explain this particular code? Well, it may happen that T1 pole after is larger than T1 pole before. This usually happens because the timer 1 counter goes into the sawtooth waveform, right? So if I'm having my T pole before somewhere over here, my T1 after, so T1 after is larger than T pole before, then the difference in counts is clearly multiplied to 3.2, the amount of seconds, more microseconds, that lapse, that you have measured in that interval, according to TCNT1 ticks, tick increments. But else, well, what happens now? You have the sawtooth, like this, you have a T1 pole before, and you go through the clearing of the TCNT1 counter back to 0, and then you measure T1 pole after, and that's the reason why T1 pole after is going to be less than T1 pole before. So that means that you need to make a correction. Effectively, you want to measure the amount of ticks that lapsed from clearing to T1 pole after, and you want to measure the amount of time that ticks that lapsed between T1 pole before until you got to its maximum count value. So this is what is essentially being done over here, and that's why we see this number in here, and now we multiply that with the number of microseconds for each tick. So, and it's again explained, so you can have a look at that once more. So this is a piece of code that I feel was kind of interesting for you to have a look at, and then find out how these different components work together. So this will conclude our ADC lectures. Any questions about this part? And if not, we'll continue with the EEPROM and the watchdog, the next set of slides. Okay. So let's have a look. Alright, so we're going to talk about the EEPROM and the watchdog timer. So in these slides I'm showing you more of the data sheet itself rather than writing it out myself, because at some point you will really be looking at the data sheet completely on your own. As a matter of fact, when you start to work on the next block, you'll be talking about, you'll be working with communication protocols, and I'll ask you to actually look at the data sheet and interpret it yourself, and then explain how you should program it. Of course, we will help you with snippets of code, but the point is that it's important to be able to read the data sheet. Now, here's a simple introduction. It says that in EEPROM has about 100,000 write-erase cycles. It's very interesting. So actually, the first time that I taught this course, no, not the first time, but one of the last times, there was a student who had his MCU, and his EEPROM was not working. It seemed like it was totally, the EEPROM was too old. So in those days we had two professors who were looking into counterfeits. So you know that counterfeit or old MCUs that are being discarded, they can get a new sort of finish, like sort of a serial number and so on, as if everything looks very beautifully and new. But the reality is that it is just an old MCU. So they actually figured out indeed, because I asked a student to give me his MCU, and they found out that that particular MCU was indeed a counterfeit. So there's actually a real problem. So if you are going to work with hardware components, well, a significant portion is actually counterfeited, it turns out. So even though this particular MCU that he bought was just like what you did, was bought through DigiKey in this particular case, right? So that happens a lot. So you can imagine how scary that is if you are working on engineering systems together that need to be very safe. They're safe critical or sensitive or whatever it is, but you need to make sure that nothing goes wrong, otherwise someone gets hurt. So you have to think about these issues, and you need to sort of have a trusted supply chain that gives you that you trust in, that you have been good relationships with and so forth. So actually defense in the United States has a certain number of trusted supply chains that they have really good relationships with and that they verify all the time, and it's almost impossible as an outsider to get into those types of chains, and that's for this particular reason actually. So having said that, so in EEPROM you should be very careful to access this. If you always access the same address in the main body of your while loop, which is this infinite loop that always goes around and around and around, then in no time you will write something 100,000 times to that particular address, and then that particular cell will be done, and you will essentially wear out your EEPROM very fast. So make sure to really control the usage of EEPROM. So what does it do? It reads in 2 cycles, and it writes in about 100 cycles. So effectively the wearing out really comes from the writes, by the way. And so reading, that's not a big deal. You can read much more than that. So EEPROM has this particular characteristics. Flash, remember that we put the program instructions into Flash, and we saw that by adding this library in one of the earlier blocks, if you add a library that allows us to use this program space where you store the program instructions effectively, you can actually also store some data in there, and then you can read from it. So you only read from Flash, it reads in 2 cycles. And then you have RAM, which is read plus write in 1 cycle each. That's sort of a comparison. So the data though in the EEPROM remains. So even if you pull the chip out of the board or turn power on and off and so on, so the data in here survives, as opposed to RAM over here. So that makes EEPROM very interesting to store data or current state of your execution in case you need to go into a sleep mode or you need to go and reset your device. Things like that. So you can use EEPROM to take a snapshot of your state, store it in there, so next time when you start it again you can pull out that information that is needed. So let's have a look at the data sheet. So we have an EEAR high and low, and effectively that is being used to store an address that you're interested in writing or reading. In this particular data sheet, they talk about even 10-bit address space, but that's conflicting with the 9 bits here, so I assume that this particular field has an EEAR9 available, so that you can really fill up a 10-bit address space. But you put your address in here, and then there's a data register from least significant bit to most significant bit, and that register is really used as I would say similar to when we talked about the U-word, you have a register that can be used in 2 ways. You can write to it, and then the U-word will transmit that, or you can read from it, and then the U-word connects that register effectively to what you read over the U-word channel. Now, this is a little bit different in the sense that this is just one register. In the U-word you have the UDR0, I believe, that if you write it, it connects to the physical receive buffer, and if you write to it, it connects to the physical transmission buffer, so those two are really distinct. But over here you just have one register, and if you read from it, then in here you will see the data that corresponds to what is stored at this address. And when you write data to it, then you will write the data to the address that is stored over here. So that's how you would work this. Now, you have a control register, and it's a bunch of fields again, so we try to interpret it. So you start to learn how to read these data sheets more and more and more. So let's look through this. So what is this? EEPN1 and EPN0, those two are really about the EEPROM programming mode bits. So what can you do with this thing? So there's a little bit of text over here. You quickly want to move through, you quickly want to read this, but there are certain possibilities. It's possible to program data in one atomic operation, or to split the erase and write operation, for example, in 2 different operations. So if you write to EEPROM, you first erase it, and then you write the data value. And you can split that in 2 separate components, as opposed to having it done in one atomic operation. So different choices, and this particular table tells you what is possible. So here it is. So we do the erase and the write in one operation, 3.4 milliseconds. It's actually quite significant. Erase and write possibility. So I explained this earlier. So effectively, one can do sequential writes before an erasure, just if you're interested in this particular thing. So during a write, one can only flip bits from 0 to 1, so that's the restriction. If a bit needs to flip from a 1 to 0, then you need that erasure operation before you do a write. But there's some kind of interesting ways of making use of this in a way that allows you to make optimal use of the endurance of your EEPROM by using some kind of coding techniques. So the lifetime is about 100,000 0 to 1 write and 1 to 0 erasure cycles. And sequential writes before an erasure are definitely possible, and the lifetime is then not unnecessarily shortened. It's really about those erasures that will kill you, or that will stop the EEPROM at some point. Okay, so you will see in the data sheet long pieces of text like that, and you have to find yourself reading this and go through it. We'll focus here about this part. The following procedure should be followed when writing the EEPROM, and that contains a bunch of steps. Some 2 are optional, but you need to wait till the EEPE becomes 0, which is what this particular section is about. So the EEPE field